Hello and welcome to my talk. I'll be talking about continuous and discrete self-similar Markov processes and a class of ergodic skip-free Markov chains which are related to this discrete self-similar Markov chains. Let me mention that it is a joint work with my advisor Pierre Pati and his colleague Rohan Sarkar. Let me start with the motivation. Suppose we have a squared Bessel process of index beta which is non-negative. In this case, the generator of the process is given by this differential operator which is valid at least on the set of our test functions. At the same time, we consider the discrete Barton-Deth chain whose generator is a discrete version of this squared Bessel process. That is, we have n times the discrete Laplacian plus 1 plus beta times the discrete derivative. And this representation is valid at least on the set of all finitely supported functions on positive integers. What do you know about these two generators? So these generators, G and H, they are reversible with respect to their invariant measures. That is, G is reversible with respect to x to the power beta, and H is reversible with respect to its invariant measure, which is given by the ratio of gamma n plus beta and n factorial. As a result, if we consider the semigroups generated by G and H, they can be extended as self-adjoint semigroups on the corresponding L2 spaces. Also, if we consider their spectra, then the spectra of P and Q are both continuous spectra, and both of them are equal to the unit interval 0 to 1. Now, this motivates us to ask the question whether there is a similarity transform between P and Q. So this question has been answered by Miklo and Pati. So they have shown that there is an operator lambda and lambda tilde such that P lambda equal to lambda Q and Q lambda tilde equal to lambda tilde P. So this relationship is called intertwining relationship between P and Q. Also, they provided explicit representation of these two operators. Lambda is given by this Poisson kernel, and lambda tilde is given by the gamma kernel. Moreover, these two operators, lambda and lambda tilde, they are bounded, injective, and they have dense range. However, they are not invertible, and that is why we do not have the similarity transform between P and Q, but we have intertwining relationship in both directions. They also provided an approximation theorem, that is, if X denotes the squared Bessel process and Z denotes the Barton-Deth chain, then we can approximate the squared Bessel process by a sequence of Barton-Deth chain up to scaling in time in space in Scholar-Hertz J1 topology, which is the topology of weak convergence of Cadillac functions. Moreover, this discrete Barton-Deth Markov chain, they have this property, which is called discrete self-similar property. And the motivation is as follows. So we know that the squared Bessel process is self-similar of index 1. That is, if we consider their semigroup PT, then PT is intertwined with P of alpha t via this dilation operator d alpha. Now, in case of discrete case, we cannot expect the dilation operator because the dilation operator is not defined on set of all integers when alpha is a fraction, and that is why we have another operator, which is a discrete operator given by bold d alpha. It is equal to a binomial kernel, and what is shown by them that the discrete Markov chain Qt is intertwined with Q of alpha t via this discrete operator d alpha. So this property has been named by discrete self-similarity by the same authors. Now we ask the following question. So we know that the squared Bessel process is a self-similar Markov process. So what if we deal with a general self-similar Markov process? Now, for a general self-similar Markov process, it has jumps. So we consider only those processes which has only negative jumps, that is the spectrally negative processes. In this case, the generator of the process is given by this operator, this integral differential operator. Now this part corresponds to the diffusive part, and this part represents the jump of the Markov process. So Our main question in our work is whether we can find a class of discrete Markov chains which are also discrete self-similar and they are intertwined with the continuous self-similar Markov process. So in this expression of generator, this measure pi is called the Levy measure, which has this constant. And to each of these self-similar Markov process with all the negative jumps, we can assign a function phi, which is called Bernstein function, which is given in terms of these parameters m, sigma square, and pi, which also appears in the expression of the generator. Now, here how we construct the discrete counterpart of this self-similar Markov process. So we define h phi, which is defined to be this discrete operator plus an additional part. So here, when sigma square is 1 and m is 0, this is same as the generator of the discrete Barton-Tate Markov chain. And this part appears due to the presence of jump in the self-similar Markov process. Now here, this kernel h by nm is given by this mixture of binomial probabilities and the Levy measure. Now we do not have a very specific intuition behind this expression, but we suspect that this Markov chain should be related to fragmentation coagulation process, and we are still working on that. Let me mention that this Markov chain does not jump more than one step above because this kernel h by nm is 0 when m is strictly bigger than n plus 1. And that is why we call this Markov chain a skip-free Markov chain. Now here is the main result we have. We first show that this discrete operator indeed generates a failure Markov semigroup on set of all integers. Moreover, the discrete Markov chain is intertwined with the self-similar Markov process in the continuous case, and the intertwining operator lambda is given by the same Poisson kernel. Then this discrete Markov chain has the discrete self-similar property, and finally we show the same convergence result, that is the self-similar Markov process can be approximated by a sequence of the discrete self-similar Markov process by properly scaling time and space. Now here, next we want to do, we want to construct a class of ergodic Markov chains which are related to this discrete self-similar Markov chains. So here is the motivation. So suppose we have the self-similar generator, that is g phi in the continuous case, and we subtract this differential operator. It is known that this operator, which is denoted by L phi, it denotes it generates a Markov semigroup, which is called the generalized Legge semigroup, and it has been extensively discussed by Pierre Pati and Ladens above. But they have shown that this generator L phi generates a failure Markov semigroup K phi, and it has a unique invariant measure nu phi. In fact, it has a unique invariant distribution, and this invariant distribution is moment determinant, that is, it is determined by its moments. And also, when sigma square is strictly positive, then this Markov semigroup converges to its equilibrium measure at an exponential rate. Now, what we want to do, we want to prove the same results when we replace this continuous Legge semigroup by a discrete Markov chain. So here, how we construct the discrete counterpart of this process. So you replace the generator of the self-similar Markov process by the discrete self-similar generator, and we replace this operator x times f prime x by its discrete counterpart, which is n times fn minus 1 minus fn. So here is our result. We show that this discrete operator generates a failure Markov semigroup on set of all integers, and it has a unique invariant distribution n phi. Moreover, n phi is also moment determinate. And finally, this discrete Markov chain R phi, which is ergodic, it is intertwined with the generalized Legge Markov process via the same Markov kernel lambda, which is given by the Poisson kernel. Now let me mention that this Markov chain RT, it is, or this discrete Markov chain is self-adjoint if and only if the Bernstein function phi is equal to sigma square z. That is, when it does not have any jump. Now, because we have an ergodic Markov chain, so the question is, how can we find the rate of convergence to its equilibrium? Now, the rate of convergence to the equilibrium is usually given by the spectral gap of the Markov chain, and therefore we need to determine the spectrum of the process. So here is our result. So if we have this semigroup of the discrete Markov chain, then what we have shown that the point spectrum of this discrete Markov semigroup, as well as the point spectrum of its adjoint, both of them contain these numbers, exponential of negative n times t. And when sigma square is positive, that means when the diffusion is present in the Legge semigroup, then we have a spectral expansion for the discrete Markov chain. Now here, p and phi, those are the eigenfunctions of this semigroup corresponding to this eigenvalue. And v and phi, they are the co-eigenfunctions or the eigenfunctions of the adjoint semigroup corresponding to the same eigenvalue, exponential of negative n times t. Now, in particular, when phi is equal to sigma squared times z, then we, Pn and Vn, they are identical, and therefore we have the usual spectral expansion for the self-adjoint semigroup. Now, because we have this spectral expansion when sigma square is positive, we can derive its rate of convergence. That is, when sigma square is positive, we show that this discrete Markov chain converges to its equilibrium measure at an exponential rate. So here, this constant c, it is equal to 1 when RT, this semigroup, is self-adjoint, but when it is not self-adjoint, c may not be equal to 1. Now, in some restricted cases, like if we assume that sigma square is positive as well as the Levy measure has finite mean, then we can explicitly compute the value of c in terms of the Bernstein function phi. Now, these are the all riddles that I wanted to discuss. Here are the references. The first reference is on this paper by Rohan Sarkar and Pierre Pati, where they have discussed about the intertwining relationship between continuous and discrete Bessel processes. And the second reference is on the generalized Legge processes by Pierre Pati and Sabov. Thank you for watching my talk, and I hope to see you in the discussion session.